Hello, I've got three sequence and series type IB style problems to explore here. I'm going to go rather quickly, so feel free to pause at any time and read what's up on the screen. But I just wanted to draw to your attention that the main purpose of this is to show how use of proper notation will really help in organizing and sort of controlling the direction of your work. So in this first case, we have to take the given information. We know the second term of an arithmetic sequence is 7. And the sum of the first four terms of the arithmetic sequence is 12. Now the first thing I do is I write a sequence of four numbers where the second term is 7. Now that's too many variables already to work with, so what I'm going to try to do is to take some information and use it to narrow my variables. The big key here is arithmetic sequence. So basically from 7 I could subtract the common difference and get to A, and I could add the common difference and get to B and C. So in other words, you can express A, B, and C in terms of multiples of the common difference away from the second term, which means if we take the second piece of information that the sum of these is equal to 12, its rest is just a simple algebra problem. So now I know the common difference is -8, and that means if I was to work backwards, add -8 or subtract -8, I would have 15 for the first term. That means that the four terms of my sequence are 15, -7 rather, -1, and -9. And to make sure that my work and my thought process is valid, I add all four terms, and sure enough, I get a sum of 12. So, again, the key here is recognizing our use of notation, understanding how to unpack an arithmetic sequence in terms of common difference relative to the number of terms we have. Here we can see the same thing in action. We know that the ratio of the fifth term to the 12th term of a sequence in an arithmetic progression is 6:13. So what we have to do is express the fifth term and the 12th term in terms of arithmetic progression terms. So the fifth term is 4 times the common difference added to the first term. The 12th term is 11 times the common difference added to the first term. So I need to put those into a ratio and get a 6:13 result. By substitution, now I have a two-variable equation, but it is in ratio form, so I'm going to cross-multiply, distribute, collect like terms, and now I have that the first term is equal to double the common difference. So I don't know what the first term and the common difference are, but I do know that they are proportional, direct variation. So now I go to the second piece. The product of the first term and the third term is 32. Okay? I got to make the first term and the third term. When I multiply them together, I'm going to get 32. I don't know why this says 13. So we're just going to fix that really quick. Oops, that doesn't do it. Alright. And C. Alright, keep going. What I did now is I have U1 times the third one, which is U1 plus twice the common difference, and I distribute, and I get this equation. Once again, it's a two-variable equation. Thank goodness I have a proportional relationship over here. I'm simply going to substitute everywhere I see a U1. I'm going to put in a 2D, as seen, and solve for D. Now I have plus or minus here, but since all the terms are going to be positive, if D was -2, we would eventually run into negative terms, especially by the time we got to 100. So we're going to assume positivity here, and we get U1 is twice the value of D, and that's 4. So clearly if D was -2, it wouldn't take us long to get negative terms way before we got to 100 terms in the sequence. Anyway, we have now the first term is 4, because it's twice the common difference of 2, and so that would produce a sequence. Now instead of adding those up, the first 100 terms, we can remind ourselves that there is a Gaussian little formula trick here. This is a variation of it, where all we need to know is the first term and the common difference, and that produces 10,300. Or if you know the 100th term, which you can find using our formula, you add those together and you divide by half or multiply by half the number of terms, and you get the same result. So this first result is really a shortcut, preventing us from having to find U sub 100. We just substitute the common difference and initial value, and we get all our money. Alright, next, last problem. This time we're dealing with a geometric sequence. And we have the sum of an infinite geometric sequence, and it's 13 and 1/2. The sum of the first three terms is 13. That's kind of interesting, isn't it? You add up everything in the sequence to infinity, it's 13 and 1/2. You add up the first three terms, you're already at 13. So the rest of those infinite terms are going to add up to 1/2, which means they're going to be pretty small. Regardless, I need to find the first term of the sequence. So what do I know? I know infinite sum, and that gives me the first term and the common ratio. These are the things I need to know for any kind of sequence and series problem in IB. This 27/2 is the sum that results. Well, what else do I know? The sum of the first three terms. So first term, second term, third term equals 13. Write them in terms of geometric sequences. So this time, instead of a common difference, we have a common ratio. We're going to multiply the first term by r, and we're going to multiply that result by r again, and that gives us our three terms, which is a quadratic polynomial. But we don't know u1, nor do we know r. So I'm going to have to go back to what I know and express one of these variables in terms of the other, after I factor out the u sub 1. So now, clearly, to solve for u sub 1 is the way to go, because I factored that out, and then I won't have to square if I substitute in for r. So this is u sub 1 in terms of r, expressed down here instead of u sub 1. Now we have what's going to turn out to be a cubic polynomial. And normally when you see cubic polynomials, the reflex or the instinct is to go for a calculator. If you are taking a IB exam and you don't have a calculator and you see a cubic, chances are something miraculous is going to happen. Some recognize this, others don't, but regardless, if you multiply r minus 1 times the r squared plus r plus 1, you get the difference of two cubes. So this is the factoring formula for difference of two cubes. So that gives us a nice solvable equation. We add r cubed and subtract 1, or 27, whatever, you get it. I got r equals 1/3, just to make sure, because I don't want to go any further into this problem until I know I'm right. I actually rearranged this and made 13 over 1 plus x squared as one of my equations, and I looked for the intersection of 27/2, 1 minus r, or 1 minus x here. So when they intersect at x equals 1/3, which is what I got my solution for r. Now I make sure I answer the question. It asks us to find the first term. All we have to do is take 27/2 times 1 minus 1/3, and that equals 9. That's from this up here, based on the fact that the sum is 13/2. So the other thing that I could do here is just to verify. I would show that 9 times the common ratio is going to give us 3. And we multiply that by the common ratio, and we're going to get 1. Notice that 9 plus 3 plus 1 adds up to 13. And what we're going to do after that is add 1/3, and 1/9, and 1/27. And we can see that it doesn't take very long for the continuation of this sequence to give us inordinately small numbers. And the sum will eventually be 13 and 1/2. So all of this other stuff is equal to 1/2. Alright, thanks for watching. Have a good day.